I'm Fatima Ebrahimi from Princeton University, Princeton Plasma Physics Laboratory, a physicist with years of experience in fusion energy and also the plasma physics with application to space and astrophysics. Also, I'm the inventor of magnetic reconnection drive, MRD thruster, which before I start, I would like you to have two takeaways from this presentation. One is that MRD thruster originates from this long history of fusion research at Princeton. And second, if successful, MRD enables many of the space applications that sometimes are referred to emerging market opportunities. So starting with the challenge is that for long-range travel, speed and fuel efficiency is really critical. And next generation of rocket thrusters are required for shortening the trip time for space travel. And the reason for that is that the conventional chemical technology is fuel inefficient. That means that only a tiny fraction of the initial mass is payload and the rest is fuel. And that causes that these rocket technologies are going to be very costly. And however, MRD is fuel efficient. For example, for a specific mission to moon with conventional technology, chemical technology, 8 fuel units is needed, while with MRD only 1 fuel unit is required. So therefore, with MRD, we can tap into the emerging markets for shipping small payloads to moon and beyond. So let's start just with a little background because I'm a physicist. So that MRD is inspired by the way that how solar flares are formed and how plasma, this conducting gas, is formed and accelerated on the surface of the sun through a process is called magnetic reconnection, where magnetic energy is converted to kinetic energy directly. And in fact, to the right, you see that we have replicated this process in a laboratory experiment in Princeton, where these magnetic rings are produced and are accelerated to really high velocity. So this is the foundation of MRD, a brand new way of acceleration with magnets. And to the right, you see our novel prototype design for MRD with magnets and the thruster vessel. That plasma is generated and produced and accelerated in the vessel. And to the left, you see how these magnetic bubbles or plasma bubbles are being attached from the back of the rocket, and the rocket is propelled forward. So MRD is an electromagnetic product, means that we can take advantage of new disruptive technologies such as high temperature superconducting magnets. Which have been used, the HTS have been used for fusion energy application, and we want to use that for space application with MRD because that's the perfect place to actually use it. It's a perfect product for space application. And also, I should say that plasmas for space propulsion have been used in the last couple of decades via electric thrusters. However, the disadvantage of electric thrusters are that they produce really small amount of thrust. But with MRD, we can combine this speed and power. And as you see to the left, that it's a parameter space that MRD can cover this gap in terms of parameters, power and speed, that existing technologies that are fuel inefficient, as I mentioned, chemical rockets, and also electrical propulsion, that they are only produce a small amount of thrust. But with MRD is fast without sacrificing power. So therefore, MRD can be used to deliver supplies from lower orbit to moon for a future moon base. And is 2 to 4 times faster than electric thrusters, 10 times faster than chemical thrusters, and other application could be for asteroid mining and planetary defense, and eventually for the whole interplanetary space exploration. So here I am putting the comparison with existing technology in the column in orange, with the advantage of MRD, which is power scalability. The power can range from hundreds of kilowatt to megawatts, and also is fuel efficient. As I mentioned, it's faster than existing technologies several times, and it produce large thrust. And the most important thing is that it's fuel flexible. That means that it can use light fuels, light atoms like hydrogen, in comparison with the existing technologies that usually use very heavy gas or actually chemical fuel. And MRD is compact in terms of engineering, is simple without moving parts. So therefore, the lifespan of this product is long, and it has a large potential market. So for commercial pathway, we want MRD thruster to license that to space companies who can handle the manufacturing. The key companies, to name a few, is Blue Origin, SpaceX, for example, or Northrop Grumman. And here is the roadmap of our product and also our funding. So we have been able to secure non-dilutive funding from DOE to build the bench type prototype of MRD, to do detailed engineering design, assembly, procuring part, and also for operation, basically for initial concept demonstration. However, for building the full-scale prototype, in particular, doing lots of testing, additional testing, we need additional funding. That's why we are forming a company, and for also raising additional funding through angel investment and venture capital in parallel. So the team is PPPL team, Princeton Plasma Physics Laboratory, for benchtop development of this MRD, and PPPL is the ideal home for this development because of the rich history in plasma physics and also related engineering. So to the right is my engineering team that working with me to develop the benchtop prototype. So we are looking for company C-suite, also more industry and space connection for short-term, specifically for short-term application, and also additional angel funding, as I mentioned, for a full-scale prototype and more realistic testing, and in general for guidance for bringing a full-scale prototype to market. And thank you for your attention, and thank you especially Equalize, and also a special thank to my mentor, Manny Stockman. Thank you.